Hey guys, Mrs. O'Donnell here. So unfortunately with this exploration, it was hard to get it into a 15-minute video. So this is our multiplying polynomials special products video part 2. All right, so let's just dive right in. Similar to that first exploration, go ahead, take a minute, pause the video, try some of these on your own, see what kind of patterns you might notice or shortcuts you think you might be able to make a conjecture, write it down, and then watch the rest of the video to see if your conjecture is accurate. So go ahead and do that now. If you want to pause it, go ahead and pause now and give these a try. All right, so if we're checking it out, we're using our box method or our area models to do our multiplication. Okay, so if we're looking at our tables below and just kind of seeing what I notice, before we were working with perfect squares, right? Our factors matched exactly. Well, now what I'm noticing is that my factor pairs almost match, except they have opposite signs, right? I have a plus and a minus, a plus and a minus, a minus and a plus, 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 a plus and a minus and a plus. Okay, so it's going to be a little different. I can tell already it's going to be a little different than the last pattern that we were looking at where we were multiplying perfect squares. So now I'm going to approach it the same way. I'm going to use my box. I'm going to come up here so I have a little more room. And I'm just going to multiply out. So I've got x plus 1, x minus 1, right? So x times x, that gives me x squared. X times 1 is 1x. X times negative 1 is negative 1x. Negative 1 times 1 is negative 1. And I'm going to go through and I'm going to combine my like terms. So negative 1x plus 1x, well, that gives me 0x. So I have x squared minus 1. All right, now I'm going to go ahead and do the same thing for my next one. Let's see here. I've got x plus 2, x minus 2. So x times x is x squared, x times 2 is 2x, x times negative 2 is negative 2x, and 2 times negative 2 is negative 4. So let's see here. That leaves me with x squared. 2x minus 2x is 0 x's. So that cancels out. I'm left with just a minus 4. All right, let's try another one. Let's see here. So I've got, sometimes the small boxes make it kind of hard to see, but I'm doing my best. Oh, x minus 3, x plus 3. So we've got x times x, that gives me x squared. X minus 3, or x times a negative 3 is negative 3x. X times 3 is 3x. 3 times negative 3 is negative 9. And let's see here, that leaves me with x squared, negative 3x and 3x. Well, that leaves me with 0 x's. And then I've got a minus 9. All right, let's do another one here. So I've got 2x minus 1, 2x plus 1. So 2x times 2x, that gives me 4x squared. 2x times negative 1 is negative 2x. 2x times 1 is 2x. 1 times negative 1 is negative 1. So I've got 4x squared, negative 2x plus 2x. Well, that gives me 0x. And then I've got a minus 1. At this point, you might be able to start seeing the pattern already. So if you see the pattern already, make a conjecture and go ahead and try this next half of the problem set using the pattern, and then check your work by using the area model. Okay, so let's do that. Let's see here. Next, the pattern that I think I see is that I'm going to, if I have a plus b times a minus b, I end up with a squared minus b squared, or the square of the first term minus the square of the second term. All right, so if that's true, then let's see here. I would end up with x squared minus 4 times 4 is 16. All right, so let's check that with our area model, right? X minus 4, x plus 4. So x times x is x squared. X times negative 4 is negative 4x. 4 times x is 4x. And 4 times negative 4 is negative 16. And our middle terms would cancel out or add to make 0x, which would leave you with x squared minus 16. So far, so good. Let's try it with our next one. X minus 5 times x plus 5. If I use my pattern, I would have x squared minus 25, right? And I could go ahead and check that by using my area model, right? X minus 5, x plus 5 gives me x squared, negative 5x, 5x, and negative 25. And those middle terms would add to make 0x's. Let's see here. Let's do another one. So using my pattern, I see x squared minus 100. So let's see, test it out using my area model just to verify. X plus 10, x minus 10, x times x is x squared, x times 10 is 10x, x times negative 10 is negative 10x, negative 10 times 10 is negative 100, right? Those middle terms would add to make 0, leaving me with just x squared minus 100. Cool. All right, last one here. I'm going to try this out using my pattern. So let's see, 10 squared is 100x squared minus 25. And let's just verify that using our area model. 10x minus 5, 10x plus 5. 10x times 10x is 100x. 10x times negative 5 is negative 50x. 10x times 5 is 50x. And 5 times negative 5 is negative 25. So that would leave me with 100x squared minus 25. Awesome. So far, so good. All right, so we've got this other special pattern here. So when you have two factors, two binomials that are being multiplied together that have opposite signs, but your terms are sort of matching terms, then you have this difference of two perfect squares, right? Where you end up with that, those middle-like terms add to make 0, or they sort of eliminate one another. All right, so can you think of a new shortcut? Describe your shortcut and how does it work? All right, so the new shortcut that we came up with is we said that when we have two polynomials with matching terms but opposite signs, that we square the first term and square the last term with a subtraction sign between them. Let's see here. Give two other expressions in factored form that will work with your new shortcut. So for example, if I had x plus 17 times x minus 17, that should work. Or another example would be if I had 3x minus 5 times 3x plus 5. That should also work. Okay, so let's check it out. Will our new shortcut work for x plus 1 times x plus 1? Well, no, that won't work because we don't have opposite signs there. We have plus signs for both of those. Will your shortcut work for x squared minus 3 times x squared plus 3? Yes, that one should work. We have opposite signs. We have a matching first term and a matching last term. We will need to be a little cautious with that x squared. We have to really think about those exponent rules when we're squaring it. Okay, and last question here, it says, will your shortcut work for x squared plus 6 times x squared minus 6? And again, yes, this should work, right? We have those opposite signs. That's really what we needed for it to work. It doesn't matter if the plus sign comes first or the minus sign comes first. Doesn't matter, okay? But again, we want to be cautious with that x squared and really think about those exponent rules. What happens if you have x squared squared, right? This is a power of a power rule, so we would multiply 2 times 2, which gives us x to the 4th power. All right, let's see here. Will your shortcut work for 5x minus 2 times 2x plus 5? No, it will not. Our a terms have to match exactly, and so do our b terms, and they do not here. Okay, so you're not just using the same numbers, you're using the same numbers in the same order. Will your shortcut work for 3x minus 2, 3x plus 2? Yes, we will, right? My a value would be 3x. My b value is 2, and I see that I've got a minus and a plus, so I've got those opposite signs. Will your shortcut work backwards? Can you use it to rewrite x squared minus 36 in factored form? How do you know? Well, let's take a look at what would that look like if we did our area model, right? We know we'd have to have an x squared, and we'd have to have our negative 36, but we have to think, you know, what are going to be the factors. So we know x squared, that one's pretty easy. It's going to be x and x. And 36, we have to look for that perfect square. So we know the square root of 36 is going to give us 6. We have that minus sign, so we know that one of our 6's has to be negative. And then we could kind of verify it by looking. Negative 6 times x is negative 6x, and x times 6 is 6x. And when we add those, we would get 0x, leaving us just with that x squared minus 36. So yes, we can. We can use it to rewrite our polynomial in factored form. Will your shortcut work to factor x to the 4th minus 25? How do you know? Well, again, if we're not sure, we can grab that area model and sort of work it backwards. Think of it like a little puzzle. If we've got x to the 4th, we've got x squared, right? So x squared times x squared. And then we've got this negative 25, which we know is 5 times 5. One of them has to be negative, and that leaves us with this negative 5x squared and 5x squared, which those middle terms would add to make 0, leaving us with x squared minus 5 times x squared plus 5, and that totally works with our pattern. So yeah, that one worked as well. So this last part of our exploration here, this application, it says, in your own words, describe how you can identify which quadratic expressions are difference of squares. Well, to be a difference of two perfect squares, you literally have to have subtraction and two perfect squares. So if you don't have those criteria, then you don't have difference of squares, right? So x squared minus 9, yes, that's a difference of two perfect squares. X squared minus 1, those are perfect squares. 100x squared, 100's a perfect squared, x squared's a perfect squared, 1 is a perfect square. So yes, those are all perfect squares. 4, x squared, and 1, yep, that's a difference of perfect squares. All right, this one's a little tricky. X to the 4th is a perfect square. It's x squared squared, right? And then 9 is also a perfect square. The square root of that is 3. So this is also a difference of perfect squares. I don't think there's any examples here that aren't. So hopefully you're looking, do I have a perfect square in the front, a perfect square in the back, and a minus in the middle? And that tells you yes or no if it's a difference of two perfect squares. Same deal on this slide. Can x squared minus 10 be factored using a difference of squares? No, because 10 is not a perfect square. X squared plus 100, can that be factored using difference of squares? No, because it's not a subtraction problem. And x to the 6th minus 9, can it be factored using difference of squares? Let's see here. X to the 6th could be written as x cubed squared minus 9, so yes, now we have a difference of two perfect squares. Micah used a difference of squares to factor this expression. His work is shown. His teacher said he didn't factor it completely. This is what's coming, guys. We haven't started factoring just yet, but it's on the way. Thanks so much for sticking with me. Don't forget to log on and do your Google form for today, and come to office hours with questions.